Hey, welcome back to Data Structures and Algorithms. Today we're going to talk about maps. Specifically, we're going to talk about tree maps. A tree map is a map made with a binary search tree. And they are a special kind of set. So what we do is the idea behind a map is that it will have several keys, and our keys could be something like strings. And they'll take a string, like a letter, and map it to a value. So we have a key for looking stuff up by and a value that they are mapped to. Like we could map A to 7 and B to 6 or something like that. Or we could map something like Wilshire to my classroom number. And so the two main functions we want to make sure we have are put and get. Put something in a map, get gets it out. You put something with a key and a value, and you get stuff, you retrieve it out of the map with the key. And since we're using a tree map, that tree map's going to help us be able to put and get at O log in time, because we'll be looking stuff up using the quick nature of the binary search tree. But will be a set because your keys actually form what's called a key set. And if we try and put something that already has that key in it, like say I tried to put B to 17, where I got a 7, it would return the 6 to me and change what this is associated to that new value. Now, I could have multiple things mapped to the same value. I could go ahead and map B to 7 and Wilshire to 7, but I can't have two of the same key. So in that way, a map has to be a function, and that's another word for functions, are maps. So we're going to make a binary map. In Java, they have java.util.treemap, and it works exactly the same way, but I don't want to have any name collision, so I'll call mine binary map for a binary tree map. And we'll be using a private class, but I'm not going to call it node. I'm going to call it entry. And our entry is going to have a K key and a V value. So you'll notice that we're not using the standard E that you may be used to for our generics. We're using K and V because that's the traditional letters for a map, for key and value. And they're going to have a left node, which we'll call entry, and a right entries because it's going to be a linked data structure. So we'll say private entry, and our entry will take in a key and a value V. So key equals that, and value will get this one. All right, and now we need to let's see here. Do we need to do anything else with that? I don't think so at the moment. So we've got it. Basically, this is our simple node class. It's going to be storing keys and values. And the key we're going to learn will have to be a comparable because we're going to use that. Now let's make our tree. By private entry root. Remember, our entry is just like our node class, but we're just sticking with tradition of calling them entries. Public binary map will simply make my root null. And we need to work on the constructor, the put method. The put method takes a key and a value, and if it finds that there's already an entry at that key, it will change that entry's value to value and return the old value. All right, so let's start with the special case where the root is null. So if the root is equal to null, then we simply say the root is going to be equal to a new entry with key and value. And there must not have been an entry with that key already because the root was null. So we just simply return null, telling the user there wasn't something there already. That's the key. We're returning a special value. Most of the time, you'll know if something's there or not. You'll just be putting it. But it's sometimes you could say, if you're using strings, you say if your values are strings, you say string, old equals put, and you can get the old value. It also makes it easy for swapping and things like that. Right. Otherwise, what we're going to do is we're going to make an entry called current, or we're going to make a reference to current, to be more exact. And we're just going to say, I think we can do while true. We'll see. All right. If current, well, actually, let's start with the value. So if key, which needs to be comparable, so we're going to cast it as comparable. So if comparable key, so we're making it a comparable right now. Dot compare to current dot key is less than 0. So that is the case that what we're trying to add, remember we're adding based on the key. What we're trying to add is less than what we're currently comparing to. We need to slide left. So then current, we'll say if current dot left is equal to null, then current dot left needs to equal a new entry with our key and our value, and we'll return null. So this is the case where we try to slide left in our binary tree, but it wasn't there. So let's take a look at what that would look like here. So remember, each thing is a key. And just think about that, the key value. All right. So maybe we might have a key that is a number like 7. And that key unlocks a value somewhere else. Okay. Maybe that value is some sort of name or something, or a word. Let's put, some word. Okay. But we're focused just on the key. Well, we're trying to add a value. And we're trying to add 6. Well, 6 is less than 7. And so we'll come down here. But if this is null, then we've found that this key must not exist, and we need to add it. And so we don't return an old value because there wasn't one. Else, so if current.left was not null, then we need to just say current needs to slide that way. Current needs to become current.left, and we'll continue the process. All right, now we're in the condition of got to cast the comparable, and I have to do that before I can say dot compare to. If the current value's key is bigger than the key of, if the key I'm trying to add is greater than current.key, then their compare to will return a positive number. Well, why are you getting mad at me? Probably because I don't have enough parentheses. Need one more there. Okay. Then we're going to do this same kind of procedure. We're going to say if current.right is equal to null, then we have found where we need to add it. And we'll return null. Else, current equals current.right. All right, so then we'll add it if it doesn't have a right child, or we will slide right. The last case is that when we compared to, we weren't less than 0, we weren't greater than 0, we're equal. Remember, if two things are equal, the compare to returns 0. So in that case, what we need to do is say, get the old value. So we'll say current.value. And then we're going to say current.value needs to equal the new value, and we'll return the old value because we actually found that value, that key already in there. We just need to reassign its value. Why is that all yellow? I'm not sure. Anyway, let me try opening it up again. There we go. Okay, so that should take care of that because we are eventually going to return at some time in this. All right. Now that is put, we have to do get. So you get things based on a key. And we return the value associated with it. If there isn't one there, we'll simply return null. And so you can imagine that it's basically going to be this exact same procedure here. If the root is equal to null, then we return null. Else we're going to say entry current is equal to root. And we'll say while current does not equal null, if current.key, well, actually, let's start with this. If key.compare to current.key is less than 0. All right, now it's not going to like that, though, because it doesn't know that key is comparable. So I have to cast it. Then we will simply say current equals current.left. Else if it's greater than 0, I need one more parenthesis there because you have to say do this first, cast first, then call dot. So I need parentheses around that as the key as well. All right. Else if that's the case, then current will equal current dot right. Lastly, if it wasn't less, it wasn't greater, they must have found it. Then we return current dot value. Well, if we get all the way through this while loop and we end up with a null current, then that means we just need to return null because we didn't find it. All right, we've got a put, we've got a get. Let's do a toString. Well, we could also just implement the iterator like we did last time. That would probably be best, but let's just do a simple toString. So to do the toString, I want to iterate through this map in order that they're in. So I'm going to do that. Actually, you know what? I want to be able to return a set, a key set. If we could do that, that would be really nice. Because that allows you to loop through the keys. So I think that's what I'm going to do. We've got a set right here, so we're going to do that. We're going to make something called key set. Key set is another important method. So I'm going to call this binary set of type K for keys, and it's the method key set. So I'll say binary set K set equals new binary set. And we're just simply going to go around and add to our set every one of our keys from our entry. And we could add them in any way. We don't have to add them alphabetically. So we don't have to do like an in-order traversal. We could do a level order traversal. We could do a pre-order traversal, which is what I think I'm going to do. I'm going to make a stack. java.util.deck of type entry. And dec is the interface. Linked list will allow me to do it. And I will say stack.push root. Well, if root is equal to null, then we'll just simply return return the set. It's empty. All right. Otherwise, we'll go ahead and push the root, and I'll say while not stack dot is empty. I'm just going to do a simple pre-order traversal here. So I'll say first I'll visit. So I'll say entry current equals stack.pop. And I'll say set.add current.key. Then I will slide left and add it to my stack. Well, I'll add my right first. So current.right, because remember it'll be backwards. But again, it doesn't even matter if I don't do it exactly in the right order, because it's going to be put in the right order when I add it to my set. But traditionally, a pre-order is you add right, then you add left. So we'll add the right and left child. We need to check if they're null, though, first. So we'll say if current.right does not equal null, then we will add stack. We will, stop that add. That's not right. Stack.push. Then we'll say if current.left does not equal null, stack.push current.left. Okay, that should do it. That should be able to go through and add everything to our stack. Once the stack is empty, then we're all done doing our traversal, and we can simply return the set. All right. Now that we've got that key set, we can easily do a toString. Let's do a toString. Public string toString. I'll simply say binary set of type K, keys equals key set. Is it key set with a capital S? I think key set should be a lowercase s. Yeah, we'll do lowercase s. I'm not sure. I'll have to look it up on the Google Docs, but not Google Docs, the Java Docs. Okay, so we got our key set, and then I'm going to make a string to return. And I'll say for K key in keys, because we have an iterator in ours, so our for each loop should work. I am going to fetch that value. I'll say vval equals get with that key, and then we'll say to return plus equals, and we're going to put in the value, the key, which is key dot toString plus, and usually we do like colon, and then we'll put the value. So we'll say value dot toString that was associated with it. And then I will add a comma. All right. So that will do that. Now I'm going to say if keys dot size is greater than 0. So as long as that keys dot size is greater than 0, we must have had some items that were added to this. So then I can say toReturn equals toReturn dot substring 0 to toReturn dot length minus 2. Because I'm going to take off the last two characters because I'm actually putting a comma and a space. And then I will return toReturn plus a closing bracket. All right, so we should have a good toString there. All right, let's try it out. All right, make a binary map, and I'm going to say string and integer will be my two types. Let's put, and I'll put Wilshire. Wilshire is in room 222. No. And then I'll say put, let's see here, Flather. And we'll put in 111. And then I'll say put, let's say Poloshik. And I think she's in like 121. And I tell you what, I'll put in a couple more here. Oops, wrong thing. I'll put in Wilshire. Again, and this time I'm going to put in my computer science room, which is 232, and it should return, you'll notice, 222. So it returned what used to be there, because it changed it. And let's put in one more. Let's put in, how about Lutman? And I think he's in like 108 or something like that. Okay. So we should be able to get a toString of this, and it should be in alphabetical order according to the keys. F, L, P, and then W. So isn't that cool? And that's not bad. We can also look things up, say, oh, I want to know where is Poloshik's room. And you can see that it fetches 121. If I try and find someone that's not there, maybe I'm asking for where is Cytec, I just simply get null. So that's a nice little map and how they can be used. Let's take a look at the key set, what it does. Well, the key set actually returns a set just of the keys. So you can see we have all of our keys now here. Let's take a look at the toString. And it just lists my keys. And that allows me to use elements from my key set. Let's see here, it's from set. What else? What can we get? We can... Well, usually you have to just kind of loop through all of them, actually, to tell you the truth. But we can now iterate through that binary set and get the value for each one. So let me do that right quick. I'm going to say iterator. Well, let's return iterator. So let's get the iterator. All right. And I could say next. Flather, and I can get it. And then I can say get string 1 and get his room. And that's kind of how it all works together. All right, so that's basically how the maps work. So go ahead and make this, and you can use it. You can also use java.util.treemap. That works the same way. It has a little bit more functionality. And you can solve lots of problems with this. So take care.